Have you ever stopped and wondered what's actually going on inside your phone when you ask it for directions? Well, today, we're going to trace that incredible journey of how AI went from seeing our words as just, simple text to truly understanding their nuance and meaning. I mean, think about it. We ask our phones for directions, we have chatbots write our emails. This stuff is everywhere now. But really, it all boils down to this one question. How does a machine, a thing made of circuits and code, make any sense of something as messy and human as language? That's exactly what we're going to unpack. And the magic behind all this? It's machine learning. See, instead of trying to program endless, complicated grammar rules, we basically just show the machine a massive library of text and let it figure out the patterns all by itself. Sometimes it learns from data we've already labeled for it, that's called supervised learning, and other times it just finds hidden structures in data all on its own. But here's the first huge roadblock. Machine learning models, and especially the big neural networks, are completely mathematical. They crunch numbers. They don't, read words. So the very first challenge, the biggest hurdle, was figuring out how to translate our world of text into their world of pure numbers. So that was it. That was the first great challenge. How do you crack the code? How do you possibly translate all the richness and complexity of human language into the cold, hard logic of numbers? Well, the solution, the big idea, is a concept called text embedding. The best way to think about it is like creating a unique numerical fingerprint for every single word. That fingerprint is called a vector, and this whole process is the bridge that connects our language to a machine's brain. Okay, so one of the first attempts at this was a method called one-hot encoding. It was pretty simple, but kinda clunky. Imagine you have a vocabulary of 10,000 words. Well, each word was represented by this giant list of 9,999 zeros and just a single one in a unique spot. It gave every word its own address, sure, but it was super inefficient, and more importantly, it was missing something absolutely crucial. Right, and here's the problem. Methods like this saw words like apple and orange as completely unrelated. As far as the computer was concerned, they had nothing in common. It had no clue they were both fruits. So it captured the word, but it completely, totally missed the meaning and all the relationships between words. So clearly, just assigning each word a number wasn't going to cut it. The next great leap forward had to be about moving from just code to actual context, teaching the machine not just what a word is, but what it really means. So, what if those numerical fingerprints, those vectors, were so good that they actually captured the relationships between words? So good, in fact, that you could do math with them? Like, literally, word arithmetic? And this is where things get completely mind-blowing. Models like Word2Vec figured out how to create these vectors where you could do math with meaning. The vector relationship between king and man was almost identical to the one between queen and woman. This was proof that the model wasn't just memorizing words, it was actually mapping out the abstract concepts of gender and royalty. Incredible. This breakthrough just opened the floodgates for all these new deep learning models. We started getting things like recurrent neural networks, or RNNs, and their more powerful successors, LSTMs. Their big innovation was a kind of memory. They could finally process words in a sequence, which let them understand the flow and the structure of an actual sentence. But then, in 2017, everything changed. A new architecture was introduced that would become the foundation for pretty much all modern AI. It was called the transformer. Now, what's so wild here is the totally different approach. You see, those older models read a sentence one word at a time, kind of like we do. But that meant they could actually forget the beginning of a long sentence by the time they got to the end. Transformers, though, they look at the entire sentence all at once. And this superpower is called the attention mechanism. It lets the model weigh the importance of every single word in relation to every other word in the sentence, no matter how far apart they are. It's how it knows that in the sentence, the robot picked up the ball because it was heavy. The word it refers to the ball, not the robot. And the impact was just explosive. The pace of innovation went into overdrive. Just 1 year after that paper, Google released BERT. The very next year, OpenAI dropped GPT-2. Seriously, every major generative AI tool we use today, from Gemini to ChatGPT, they all stand on the shoulders of this one single breakthrough. Okay, so now we have these incredibly powerful language models. But how do we actually turn them into these smart, knowledgeable chatbots and assistants we talk to every day? Well, the key is a technique called retrieval augmented generation, or RAG for short. You see, a language model by itself only knows what it was trained on. RAG basically gives it a library card. It allows it to look up fresh, relevant info from an outside source before it even tries to answer you. So picture this workflow. When your question comes in, it doesn't go straight to the AI's brain. First, it triggers a search in this specialized knowledge base, which is called a vector database, to find all the chunks of information that are related to your question. So the process is actually pretty simple. You ask a question. The system then finds all the relevant context, and then it hands both your original question and all that extra context to the language model, and basically says, okay, use all of this to give the best possible answer. This is what makes the AI's responses so much more accurate, up-to-date, and trustworthy. And you know, these vector databases really are the unsung heroes of this whole thing. They are like hyper-efficient digital libraries. They store those numerical fingerprints, the embeddings, for millions of documents, and they're built for one single purpose: to find the most relevant context for an AI in the blink of an eye. And this isn't just theoretical stuff. Companies out there right now are using tools like ChromaDB, FAIS, and Pinecone to power their AI apps. It's what gives them the ability to draw on these massive private data sets to answer our questions with incredible precision. So when you step back and look at it, in just a few short years, we've gone on this absolutely incredible journey. We started with the basic problem of just turning words into numbers. Then we got models that could grasp context with attention. And now we have these sophisticated systems that can actively research answers in real time. It's been a truly remarkable evolution. And it leaves us with a final question that isn't really about technology anymore. Now that machines can finally understand us, what do we want to say to them? What new frontiers of knowledge will we explore together?